Alright, so here's going to be another version of the lecture on visual hypothesis testing. Hopefully this one will have much better audio, but has the misfortune of not having the live classroom interaction, which was kind of useful for hypothesis testing. So I've adjusted the slides slightly so that we can be able to see the answers more easily rather than flipping back and forth between the slides and R. So here we go. So I'm interested in comparing distributions still. And in the previous lecture, we looked at population pyramids, looked at them in ways of comparing countries, and it's effectively having back-to-back histograms based on the age distribution of the population of that country. And just remember, this is Canada, which has got a shape that's kind of this muffin shape, which is typical of Western democracies and their population distribution. It's got lots of interesting features. You can see the population bulge that is around the baby boom, the tail end of the baby boom. And you can also see that there's a rough symmetry between the sexes, males and females, being slightly more males than females early on, and then towards the end of the lifetime, since males have a shorter lifetime than females, a much shorter bars here for these higher age groups, because women tend to live longer. But mostly it's fairly symmetric. The differences in themselves are kind of interesting. So we looked at that as typical as I said, a Western democracy population demographics. And here's another we looked at in Saudi Arabia. You think about, well, how is this different? It's clearly got a different shape. The bulge in the population is much lower age, the sort of widest part of this thing. It is, again, tails off. Lower values here proportion of people living to be higher age, likely due to lower life expectancy in Saudi Arabia than in Canada. But you also see that there's kind of the same shape on either side, but there's definite asymmetry, and that there are a lot of males, many more males appearing in Saudi Arabia data than there are females. And so that's interesting itself, what makes Saudi Arabia different from Canada, that we see that kind of asymmetry between the two back-to-back histograms. We look at Bahrain. Bahrain is another state in the Middle East that has, again, the sort of bulge that's much lower down. The bulge of the age group is between, the 20s to 30s, and the asymmetry here between males on the left and females on the right is quite stunning. That these two distributions look very, very different back to back, although they have similar places where they bulge out and how they tail off in either tail. So you might ask, well, what's going on there? So identifying that and saying that looks like something very suspicious, like what's happening, why are we not seeing any females in this population to the extent that we're seeing males? So a little deeper investigation. If you look closer at Bahrain, Bahrain's interesting in that how it grants citizenship, in that it has a lot of its population being non-citizens. So looking at their census data, the growth from 2001 to 2010, the Bahrainis grew a very small amount, but the non-Bahrainis grew by a huge proportion. Right, so there's a huge change in the population. There's an awful lot of the population is not a citizen of Bahrain. And so if we break that down and look at the non-Bahrainis, you can see this very asymmetric thing. Certainly the bulge is about roughly the same, and the children look about the same. But once we're in this age group, this employable age group, the 20s to 50s, etc., there are very many more males than females. So you see a huge bulge there. You compare that to the Bahraini citizens. The Bahraini citizens now look a lot more symmetric, that it looks a lot more like the same number of females as males. This distribution is, of course, a lot different in that there are a lot of very young Bahrainis in the population. A huge number below 20 years of age. So we don't have this going back in this muffin shape that you see as in Western democracies, but rather large base, this pyramid. And we have on the left here is clearly economic workers. These are the employable males coming into Bahrain for jobs or economic opportunities of various sorts. So that explains this overall picture that we saw here is explained by the difference in the population of Bahrainis, which are very similar on the sexes, and the population of non-Bahrainis, which are quite different on distribution on the sexes. And there being such a large non-Bahraini population in Bahrain, it's reflected in the overall population that we see up here. This has been moved to affect the overall population. Again, there being more non-Bahrainis than there are Bahrainis in the population. So it becomes very interesting to take these apart and see what's actually going on. So it's good to see, compare distributions and see what the differences and similarities are between them. And so we've looked at a number of ways of doing that. We just saw the population pyramids, which are back-to-back histograms. We could have overlaid histograms, back-to-back density functions, overlaid density functions, quantile functions, one on top of the other to compare the two distributions. And we will notice differences between these, either side, the two distributions that we're comparing. So now the next question we ask, as we, when we see huge differences, we look in and look for some explanation. But the next question we might ask is, well, any differences that we see here, should we be getting that excited about it? Are these really significant differences, or could they be explained if I just, if the two populations were, in fact, if the two distributions were in fact the same? So, a couple of things to note here, that some of these displays allow us to see some differences better than others, right? Some highlight the more meaningful, more important differences. Certainly quantile functions, you immediately see differences in scale, location, and shape. Here you certainly see differences in scale, location, and shape as well, although the comparisons are not quite as easy to make on shape when they're lined here. Here with the overlaying, that's a little more complicated to see because you can see the overlay of the alpha blending here, the blue, the differences your eyes often attract just to this dark part, as we mentioned last time. So what we want to know is, any difference that we do see, does it really matter? Is it something worthy of further investigation, like we did with the Bahraini example? The Saudi example, by the way, had a similar explanation in terms of non-Saudi citizens explaining the differences between the sexes. So let's look at this. So a very common context for data analysis to think about how might this data have arisen? How might the data values actually been generated? Do they seem to come from some well-known distribution or mechanism? Or in our cases, in the population pyramids or in those back-to-back density, etc., we might ask, could the data have come from the same distribution, from the same population? And there are lots and lots more possibilities to consider when you've got two or more sets of values. So suppose we ask the seemingly harder question first. The question is, could the two sets of values be generated by the same mechanism or distribution? So we can begin with saying, suppose that they have been generated from the same distribution. This is our hypothesis. Suppose that that's the case. What does that imply about our values, right? Well, one consequence would be that the values assigned to either set is arbitrary. They could have just as well been assigned to one set or the other if they came from the same distribution. So in some sense, they're exchangeable. Which distribution this particular value comes from is exchangeable. It could have been either one. So one way of assessing this is we could look at all the possibilities. And what are the possibilities? If we have two sets of numbers, we might think of two sets of values of numbers. We might think of combining them into a single set, jumbling them up, shuffling them, and then separating them at random into two different sets and see whether or not that looks something like the data that we had. So we could jumble them all together and assign them to one set or the other, and then see whether or not they look the same as the original sets. Okay. So let's do that. Here's a function that will achieve that. So I'm going to have some data, this is my mix randomly function. I'm going to have my argument going to be some data that's coming in. The chief feature of this data is that it has two components, an x, which will be one set of data, and a y, which will be the other set of data. And they may have different sample sizes, right? So there may be different numbers of data points in each one of these sets. I'm going to put them together into a single vector. So that's all my values are put together now in the same place. And now I want to shuffle them. And so how I'm going to shuffle them, I'm going to select x values, those select values that will go into the first group. And I do that by sampling from 1 to the total number of values that I have, nx plus ny, and sample without replacement. When I take nx of those will be my new x sample, and I get that by simply selecting those values from the concatenated data, the mixed data, and then remaining values, minus select 4x, will be the other ones, and return this new data set. So my data coming in is going to look like something like this list. It's got an x and a y value, which I can read off. I'm going to shuffle it around and return a new data set with the x and y values mixed randomly. Okay. Second thing I might have is I might have some plot that I like that displays, shows the comparison between the two data sets. And so here's a simple one. Call it my plot. And all my plot's going to do is find the histogram for each of them and plot them back to back. That's what these two things are doing. One in fire brick or red color and the other in a blue color. So I could take any data. Again, the data comes in. It's got to have the first data set will be the x. The second data set will be the y component of the data. And then we'll just get the appropriate information and draw back-to-back histograms. I'm sorry, they're not back-to-back. These are overlaid, so they're going to be overlaid histograms with some alpha blending. So then I can apply this to the real data and to some jumbled up version of the data. So I'm going to try this on the South African heart data. So you remember the South African heart data, I've got either there's a family history of heart disease or there is not. So we're going to use that to distinguish the two groups. I'm going to look at systolic blood pressure for each one. So the X will be if they have a family history of heart disease, and Y will be if they do not. So my data is simply this list with the components X and Y. And I'm going to simply toss a coin, right? So I'm going to draw two plots. A plot of my data and a plot of the randomly mixed data. And I'm going to toss this coin, and if it's heads, the true data will be on the left and the randomly mixed data will be on the right. And if it's tails, it'll be the other way around, the randomly mixed data appearing first and then the my plot data. So let's do that for the South African heart data. So there they are. One is the real data showing the two histograms overlaid for the family history with and without family history, and the other is a randomly mixed of those data values of the systolic blood pressure. So the question is, do they look the same or not? You have to think, is this very different from that? And you can use your own judgments. You can see that there are some differences, right? That there are larger blue bars here, shorter ones are overlapping. That's the red bar. Longer red bar here, longer red bar there on this side, and that's not apparent over here. Well, there's some difference here. For the most part, on this side, it's almost the red one's almost entirely inside, which was the smallest sample size anyway. So you're seeing to see this kind of difference. So the question is, which of these is the real data, which is not? You may remember from looking at these histograms before, but if this was the first time you encountered it, it's not so clear which was the real data and which is not. Although we can look at the differences and we can talk about them. The question is, are they real or not? So, the thing is, can I make this easier? Can I improve on this process? Can I make this judgment of whether or not these things look different from one another, more precise? Well, here's a way that's called a lineup test, and the motivation is to think that we've got some criminal act is being perpetrated, and we have a person that we think may be the suspect for it. We take that person and we line them up again with four, in this case, four innocent people, and ask a witness to choose the supposed perpetrator out of this list. If they choose that person, that's the lineup test. That seems to be evidence against evidence that that person may in fact be the perpetrator of the crime. You see this in all kinds of old criminal shows, etc., and you still see this sometimes with. They often do it with photos now rather than a physical lineup, and it has its problems depending on how you construct that lineup. So, they just said this, old-fashioned police lineups, you'd be presented with a number of them, of which one was the actual person believed to be the perpetrator. And if that person cannot be picked out from the others, then that's evidence that maybe that person did not commit the crime, or at least the witness could not identify that person. Okay. So here's I've been using the language. I mean, this is effectively a simple test of significance, isn't it? I've got a hypothesis that the person that I've put in that lineup is innocent, and I mix them up here with others that I know to be innocent, and my test is, can I choose that person that's the supposed perpetrator out of the lineup? If I can, then I can do that. If he truly was innocent, I'd do that with probability 1 in 5, choosing him. So it looks kind of like a test of significance. So let's try to make that more precise by writing some code to conduct a lineup test. So I'm going to go through this code kind of in some detail just so we get a clear understanding of it. So there's our data again. It's going to come in. It's got an X and a Y, remember. Then I'm going to have two functions that I want to take in, how to show the suspect, how to display the suspect, and how to get a new suspect, generate a suspect. And then I'll have a layout, which will tell me how many suspects I want in my lineup plot. So there's the number of suspects, however many I'm going to use in this plot. If you give me a location, I'll use it. Otherwise, I'll just choose a location at random. This is where the supposed perpetrator will be standing, and these just say I need the functions. Now, to decide which subject to present at any given time, since I'm going to plot these one after another, I have to have a function that just goes on the suspect number. So I'm going to have a function called present suspect. If the suspect number is not equal to the true location, which I've already identified, then I'm going to generate new data, right? Generate that suspect and show the suspect with that data that generated. If it's not the perpetrator, right? I'm going to generate some data. And in any case, I'm going to show the suspect. So I'm either going to show the suspect of the data that is coming in here, the original data, or I'm going to show the suspect that is a generated data set. This is a little bit of a tricky business here because it relies on the scoping of R, in that this will be local to this function, and if it's not executed, this will be using the one that's outside of the function, which appears inside the scope of the lineup test. So that's just a little complicated aside here, using the scoping things, rules of R. So I'm just going to take care that I look after the parameters, and I'm going to go over all the suspects 1 to n and just present that suspect. That's it. So that's the presentation of the lineup. That bit of code right there. Now, we'd like to also know what the real where the real data is. We'd like to know the true location. So I could return the true location, but if you knew the true location, they may influence your answer. So I'm going to obfuscate it. So I'm going to do some funny things. I'm going to get a base that I'm going to use, and I'm going to get an offset. And I'm doing this in some random way, which makes it a little harder to see what's going on. What I'm going to return is a true location. I'm going to take the true location, add an offset to it, and raise that to some power. Okay, so that's my obfuscation, and I'm going to tell you what the base is and what the offset is. But that'll be enough for you to be have some difficulty in telling what the true location is, but still be able to determine it. So that's our lineup function, and it's going to take data and two functions: how to show the suspect and how to generate the suspect. So I have to fix the I want to figure out how to show the suspect, so I have to that has to accept, as you go back here, that has to accept a suspect number. So my show suspect has to accept a suspect number. So I'm just going to add that to my plot. So it's going to take data and suspect. It's going to do the histograms, overlay the histograms, and it'll add a little information about the suspect number here, which will display. So that's my plot now. Which means to do this lineup test, all I have to do is take my data, get it in the form of an X and a Y, and then just call lineup with the data. Generate suspect will be my mix randomly that we had, and I'm going to show a suspect using my plot, which will be the overlaid histograms in this case. And I'm going to have 20 of these, one of which will be the true data. So in a 4x5 display. So here we go. If we execute this, we get this. So now I've got 20 suspects. And our job here is to identify which, if any, of these histograms, these suspects, we can tell, these overlaid histograms, we can tell look very different from the others. So we want to say any one of these these overlaid histograms stand out from each other. So which one of these is not like the others. And also, since we know we're looking at comparing the pink distribution to the blue distribution, we could look at each one of these and say which one shows the greatest difference between the pink and the blue as we move along here. And if you don't recognize the data, the overlay before, because we've already seen it, you would have to examine every one of these in turn and say which one of these looks like it's really showing two different distributions. One which is much smaller sample size than the other. And so you might choose any one of these. And I'll give you an opportunity to just think about it, which you choose. It's particularly best if you don't remember what the data actually look like. And the true location is given by evaluating this obfuscation. So if you were to evaluate that, you get the actual value. So have a think about that. Choose one. And the true data is in location 2. Which unfortunately I remember what that looks like, so I would have picked this. But I would have picked that largely because I remember what that overlaid data looked like. We just talked about it. Otherwise I might have picked ones that had very large pink here. Little blocks of pink. So if you chose that, and remember it's contaminated because I already know what it looks like, the probability, if there's no difference between these, the probability of choosing the data is 1 in 20. So that kind of looks like a significance level. We could try some other displays. So instead of that my plot, I can do back-to-back density. So this is going to be a show suspect, so it needs to be a function of the data and a suspect number. And the data are always going to have an X and a Y component. And the rest of it is just as we did in the previous lecture, looking at the back-to-back densities. So calculating the densities and plotting them back-to-back. So here we go. Now to execute the lineup test using that display, it's mixed randomly exactly as before. but now I'm using the show suspect will be the back-to-back. So here we go. Now, which of these back-to-back displays looks least like the others? So you want to examine them in turn, looking at different features. So, I don't know. This I don't remember what it looks like so much. I think if I were choosing one, I might be thinking about this one just because that mode is so sharp on the pink side there, as being much sharper than the others. Alternatively, this double dip here might be a possibility. I'm having some difficulty in choosing which of these is least like the others. Although, to be honest, yeah, when you start looking at the blue side, so I have difficulty in choosing which one. So let's see what the true value is. 12. Okay, I didn't even look at that one. I was focused over here. I'm thinking of that. So for me, I could not pick the true data out of that lineup. So I've got no evidence against the hypothesis that these systolic blood pressures could have come from the same distribution. And so I can't see any difference. I didn't pick up any difference based on this particular visualization of difference between having family history or not family history of heart disease. So we can look at other displays. We'll try quantiles again. I'm going to look at a function to be the show suspect function, so it's got to be a function of the data and the suspect number. So we know that that data's got an X and a Y, which are the two samples, and then we construct the plot as appropriate. And again, I'm always displaying the suspect numbers so that we can see, have a number to choose from. As before, the only thing that changes is the show suspect function, and we execute that code and get this layout of 20 displays. Now, which of these are two overlaid quantile functions, one being the healthy, the no family history is in red, the family history is in blue, and we say which one of these looks least like the others. And so we look over them. I'm looking for, they should line up on top of each other, so that looks like a bit of a departure. These look pretty close together. That's a much larger departure. I might pick up, I think, that looks like the biggest gap. That sort of gap draws my eye. But you might narrow it down to a couple of these things. But let me say that I'll go for 11 here as the possible difference. And now we evaluate that thing, and I'm wrong too. So again, no evidence against the hypothesis that there's no difference. Certainly based on these quantile functions, I can't tell the difference. I would have picked this out, but this was generated by randomly mixing those two sets of systolic blood pressure values, and that looked far different to my eye than that one did. Okay. And so that's a protection of not knowing which one it is, because post hoc I might be looking at, oh yeah, I can see other differences, but you're kind of fooling yourself after the fact, because if I told you it was this one, you'd be telling me other differences to be looking at, etc. Or that one looks like a lot of differences. So no evidence against the hypothesis. So let's look at different data. So I'm going to separate the groups, still be systolic blood pressure, but I'm going to separate the groups depending on whether the patient themselves had a coronary heart disease or did not have coronary heart disease. So they have heart disease if they don't have heart disease, and that'll be the X and Y's before, that's my new data set. And I'll do this with the quantiles, mix randomly, new data set, and the results are this. So now I've got two sets of quantile functions, and which one of these look most different the advantage here is we've not looked at this data yet, so you should be able to make some kind of an honest assessment of which of these overlaid quantile functions look least like the others. And if I look over the whole group, I see differences here, differences here, but for my money that's the big difference. So I would pick I equals 3 here. And if we want to see the true answer, we have to evaluate this form at the bottom. Oops. This form at the bottom here, which when evaluated gives us 3. So it's correct. Okay, so that's interesting. So now I picked out the data from the 20 suspects that were presented to me. And so what does that tell you? Well, if the hypothesis is true, that there is no difference between whether the patient has coronary heart disease or not, then the chance that I would choose this one out of the 20 is just 1 in 20. So the fact that I've got that, that's a significance level of 1 in 20, or 0.05. So I've got a 5% significance level, which is some evidence against the hypothesis that there's a difference. That there's no difference, sorry, the hypothesis that there's no difference. Okay? So I can try that again with another visualization. Same data, now I'm going to do the back-to-back. If I do the back-to-back, looking at these, which one of these looks least like the others? So going over, that's, again, I seem to be attracted to the pointy things, pointy there. Just look at the tail behaviors. Boy, I'm having difficulty making a choice here. I guess if I were pushed, I might pick 10. It's largely influenced by the shape of the blue. So let's see what the answer is. You pick 1 and see how well you did. 12. Wow. So this test, same data, same person, different visualization. I could not pick that. I did not pick the true data set out of here. I went up on picking 10. So by this test, I have no evidence against the hypothesis from this test. So it seems then that depending on the visualization, it may be easier to tell these two distributions apart or not. So perhaps that back-to-back density is not such a great representation for this kind of being able to tell the distributions apart. So let's look at the body temperature of the two beavers we've looked at before. So we've got these, I think we looked at them before. We've got the body temperatures of one beaver, body temperatures of another beaver. These are different size samples, and so we're going to use back-to-back densities now and mix randomly and do the lineup test. Let's see if we can, if the density, back-to-back density, are any good for this data set. So again, which of these looks least like the others? And you're going to have to look at them all and turn, get some sense of what the overall shapes are. And oh boy, there's one. That looks very different. Okay, so there's no question I would pick 4 there as being quite different from the others. So let's see. And you can see the differences that I'm picking up. There's a difference here in the location. So the pink is located at a different location than the blue. It's also a difference in the spread. The spread is not that as large for the pink compared to the blue, whereas they all seem to be matched otherwise. And there's a far greater sense of bimodality here on the blue side than on the pink side, whereas everywhere else there seems to be bimodality on both sides. So 4 really jumps out at me for a variety of reasons. And that's the answer. So there's evidence against the hypothesis that the body temperatures are the same for the two two beavers. So certainly the density is, the back-to-back density is picking up that difference for two beavers. Let's see how the quantiles do for the two beavers here. Okay, so overlaid quantile functions. Wow, there it is. That's massively different, and we're seeing definitely a difference in the location and in the scale, the spread. Remember, the spread is going to be related to the slope and the location to the intercept, and some differences in the shapes of these two different distributions. So I would definitely pick 8 there, no question. And 8 it is. So in both cases, for the beaver data, at least, both the quantile function, the overlaid quantile functions, and the back-to-back densities are certainly picking up those large location and scale changes, which are the principal differences, the main difference that you notice. Whereas in the previous case, when we looked at systolic blood pressure for the South African heart disease, depending on whether the patient had coronary heart disease or not, the back-to-back density plots, at least for me, was not a very good assessment, but the overlaid quantile plots, I did pick out the correct answer. So we might also use box plots. I mean, box plots are not going to pay any attention to the modality of the distributions, but they are going to pay attention to the scale and the location, and possibly the symmetry. So all we need again is a function that will draw the box plot side by side, to take the data, the x and y data, and a suspect, and just generate that generate the lineup test. So here we go, and I think very quickly that jumps out at you, because the change is principally in location and scale. That's the first thing is jumping, that these box plots are misaligned compared to these other pairs of box plot. So I'd venture to say that 18 is the value. Sorry, 17 is the value. I was pointing at the right place, but I just don't seem to be able to count. So 17. So again, evidence against the hypothesis that the distribution of the two beaver temperatures is the same. So we could increase the number of displays to help, narrow down the choice. So if I look again at heart disease, whether the patient had heart disease or not as being the thing that defines the groups, and mixing randomly and using quantiles, I can produce the lineup test. And here I'm producing 80 different lineup tests. So now I'm going to go over all of these, just looking at them, as should you, and see if you find major differences between these two. There's certainly a difference I see. There's another difference, say about the same as the other one. Okay. So I've got those two. That's not the same. So if I had to choose, I guess I'd be looking at 12 or 28, and let me pick. Well, that's interesting as well. It's raining hard outside my office, which is what you may hear pelting at the windows. I think I'll pick 28, but I will hold 12 in reserve. So let's see what the right answer is. 28. There we go. Bang. So 28, that means I've picked the data out of the suspect lineup, and the probability, if there's no difference between those two systolic blood pressure distributions, the chance that I would pick that 28 is 1 in 80. So now I've got a significance level that's 1 in 80. That's much lower. So by increasing the number of plots, unfortunately they get smaller, so it's harder to tell the difference. But by increasing the number of plots, I get the possibility of getting a smaller and smaller significance level. I narrowed it down to these two. I could have said, you know, I can't decide between those two, but I've got some kind of scoping here that I did pick this one as 1 in 80, but if I'd said it's one of these two, then that's going to be a chance of 1 in 40 that would have been the correct answer. That the correct answer would have been one of those two. So you again get to have some kind of bounds on the significance level. So, finishing up this lineup test actually has a pretty familiar structure. There's a null hypothesis, and that null hypothesis is that there's no difference between the plots. There's a test statistic, and the test statistic itself is the visual representation. But in a bizarre way, you, the viewer, have also become part of the test statistic, or the discrepancy measure. So the test statistic itself is a combination of the viewer and the visualization. Some visualizations may be better than others. Some viewers may be better than others, which suggests, of course, that it's important to have training on what you should be looking for differences between distributions. What do these different visual representations tell you, so that you can look for what are the interesting features that might be important in assessing this hypothesis. Okay. It also has a significance level, and that given that the null hypothesis holds, the probability of choosing the actual data is this observed significance level, 1 over the number of suspects. So if you choose the actual data, then you have a significance level of 1 over however many displays you looked at. Right? If you didn't choose it, all you can say is that the significance level is greater than that, because you missed. Okay. We also noticed that for example, the overlaid quantile functions seem to be doing a better job than back-to-back densities. And I'd probably argue that back-to-back densities are doing better than overlaid histograms. And that suggests that some of these tests are better than others. Some of these visual representations are better than others. And in statistics, we often think about that as they are more powerful. Okay. And then the language we're going to use in the next lecture or so would be that each display in the lineup is not the original data. That's an exemplar. That's sort of a model data set coming from the null hypothesis. So it's really important that we put all of this together and recognize that that test, again back here, is a significance test. It's a visual significance test. It has all of the properties, and as long as we can generate stuff under the null hypothesis, we know the null hypothesis, we choose one of these out of the entire set, and if we've chosen the actual data set, then we now have a significance level, here 1 in 80. The smaller that significance level it is, the greater the evidence against the null hypothesis. Okay. So that's it for this lecture. This should be a little shorter than the actual lecture was. And the sound, I hope, is going to be much better.